To trickle in. They're not usually on time, but we love the folks who are already here, and we love those who will join later. And we are not only interested in for its own sake, we're very interested in applied Jewish learning as it applies to business ethics, as it applies to character development and spirituality, as it applies to the arts and matters of politics or government. And we have become increasingly, as friends here know, interested in science and Judaism, not in the age-old way of the conflict between religion and science, but rather how science can inform and deepen our Jewish experience. How these two are not at odds with each other fundamentally, but Judaism in its core is its orientation is affirming of knowledge, affirming of the role of science in our life to heal, to understand, to learn. And so we are very excited to have our second presenter here with us today in this field of science and Judaism, someone who both lives and knows Judaism, someone who serves as a professor in the field of science. Our topic today, the habitability of our nearest exoplanet neighbor, and what does it mean to you? We're here with Professor Evgenya Shkolnik, who's a professor of astrophysics at the School of Earth and Space Exploration at Arizona State University. She's an expert on exoplanets and stars, including the sun. She studies stellar activity and star-planet interactions using telescopes on the ground and in space to answer questions involving stellar evolution and planetary habitability. Professor Shkolnik continues to execute new observations with existing telescopes, both on the ground and in space. She is also now designing new small space telescopes dedicated to these experiments. Please join me in welcoming Professor Evgenya Shkolnik. Thanks so much for being here.
Thank you. Hi, everyone. I'm sorry we can't all be in the same room because that would be extra fun. All right, well, thank you for the invitation to talk about my favorite topic, and I would say topics, because I've been studying the habitability of exoplanets for a long time, even since my grad school days, which was a long time ago back up in Canada. But it was in fact my graduate, even though I have a very deeply rooted Jewish upbringing and I went to Jewish day school and such, I was not raised in a very observant family, but it was actually my graduate school experience that led me further to explore the observant side of Judaism and become much more observant than how I was raised. So for me, the topic of science and religion is highly intertwined, and I think that we have lots to learn from both, certainly, and I delve deeply into both. However, for this talk, I'm going to spend maybe about 20 minutes or so, or 30 minutes, talking about the science behind the search for habitable planets. I'm trying to understand what exoplanets are. These are planets around other stars. So any planet that we know of that orbits a star other than our sun is by definition an exoplanet. So if it orbits our sun, we call them planets. If it orbits other stars, it calls it exoplanets. So I'm going to talk about the science behind the discovery of exoplanets and the assessment of their potential to host life. And then I added to the title, and what does this mean to you? And that's where you come in. So that's a question for you guys, right? What the search for habitable planets and the potential discovery for extraterrestrial life means is a personal question. And I can answer it from my perspective, and I'm hoping to hear from you and from Rabbi Shmuley to give perhaps a more, a deeper Jewish understanding of this, since I am not a scholar in that realm, and maybe some of you are. So I'm looking forward to discussion. So I'm going to try and not take up the full hour with just my talking, because I really want to hear from all of you and have an open conversation about what it really means. Okay. And then I don't know, maybe AJ, if you are monitoring the questions, because once I start my talk, I won't be able to see, but feel free to interrupt with questions. I certainly don't want to lose anyone if I miss defining some astro jargon, so just stop me and we can pause. So I'm not going to see the questions, but I'll count on you, AJ, to stop me, okay?
That sounds great.
Okay, great. Okay, so let's move on. So long before the discovery of exoplanets, people have been thinking about the role of astronomy and extrasolar planets through the realm of philosophy. So I'm sure you all know who the Rambam is, Moses ben Maimon, and back in the I guess in the late 1100s, he wrote this in his introduction to the Guide for the Perplexed. You will certainly not doubt the necessity of studying astronomy and physics if you are desirous of comprehending the relation between the world and providence as it is in reality, pardon my typo, and not according to imagination. Right, so this is a very early guide, a very early direction that Maimonides, who was in his time an astronomer, at least as much as we understood about astronomy at the time, and a physician way back when, but he already really understood that understanding the truth in the physical world is in fact a window into the truth of the spiritual world. And I often point to this quote whenever people, especially observant people, say to me, why study astronomy? Like, how is that even, what's the point of that? And why would you spend your life doing this? And I can always point to and count on the Rambam to share some of this. Now, if you fast forward a few hundred years, you know, he was not the only philosopher to discuss the role of astronomy. Many philosophers certainly did. But I think the first philosopher to truly encompass or truly discuss the role of exoplanets in extraterrestrial life, it's credited to Giordano Bruno, who was a philosopher and a lapsed Dominican monk. And there's probably not a coincidence at all that we had Torah scholars and Christian monks who were thinking from the religious standpoint about the role of planets, the role of the potential for extraterrestrial life, because it all comes from the same motivation to understand our place in the universe and what was created and why. And so Bruno wrote, innumerable suns exist, innumerable earths revolve about these suns, and living beings inhabit these worlds. Okay, so up until very recently, and we live in a very spectacular time, up until very recently, these kinds of questions was for the philosophers. And now, if you fast forward 400 years, we're now living in a time where we know for sure that innumerable suns exist. We know that there are plenty of stars, but now we know that there are plenty of planets as well. And to date, there's over 4,000 confirmed. And here I'm showing you a plot of the year of discovery of a particular of the planets and the number of planets per year cumulatively. So we're up to about 4,000. This plot is even a couple years out of date, so there's even more now. The bars are color coded, with the green being the transit method. And I'm going to introduce you to these two methods, which is why I highlight them here. The two most successful methods of discovering the exoplanets is the transit method and the radial velocity method, and I will show you those. And finding the planets is the first step, right, into finding the life on the planets. We do not yet have a way to conceive that life as we know it could exist, say, in the atmospheres of stars. It's just too hot, or in the centers of galaxies because they're dominated by giant black holes. And so we think that life must exist only on planets. And so looking for, at least so far, and so we need to look for the planets first. And so by finding the planets is then directing us where to look for the life. So we are here in our galaxy. This is an image of another galaxy, but it's very similar to our own Milky Way galaxy. So I wanted to point out where we were in our galaxy. Let's orient ourselves on a map, so to speak. So we are here. We're certainly not that big. We're a tiny dot, about 2/3 of the way from the center of the Milky Way galaxy. And in this dot so far is all the known exoplanets. They're all in this one blue area, including, which means what that should say is, wow, all those 4,000 are in that blue little area. That's because we have not yet been able to explore the entire galaxy for planets, right? Which means there are many, many more planets than those 4,000 that I already mentioned. But also within this one is a very special one called Proxima Centauri b. Now, Proxima Centauri, as you might glean from the name, is our nearest stellar neighbor to the sun. So of course, the sun is the closest star to us, right? But the next star over is called Proxima Centauri. And it in fact does have an exoplanet orbiting around it that is potentially rocky. It's about the mass of the Earth. And in addition to that, it is in what we call the habitable zone. And I'll explain that to you shortly, where the temperature of the planet is such that surface water could exist. So our galaxy is 100,000 light years away, and we and all the other known exoplanets are in this blue dot, as I had already said. Okay, so Proxima b is going to be a planet that I'm going to be referring back to give you a sense of our very nearest neighbor. Okay, so the habitable zone. So I said Proxima b, which is the name of the planet that orbits the star called Proxima Centauri. So Proxima b, that's the name you need to remember. Orbits in the habitable zone of its star. So here I'm showing you a cartoon of the sun and the four inner planets, Mercury, Venus, Earth, and Mars. And what you see is that the Earth, I don't know if you can see do you see my mouse? I'm going to assume you do. Shout if you don't, and I'll find an alternative. And so the green zone here is what we call the habitable zone. And that's where the temperature on a rocky planet like the Earth is conducive to liquid water, which we think is a necessary condition for life. And if you go to different kinds of stars, right? If you go to a hotter star, your habitable zone goes much further out because you need to get further away from the fire to have the same temperature. And in a cooler star, you have the habitable zone closer in because you want to stay close to the fire to stay warm. And so Proxima Centauri, the star, our very nearest stellar neighbor, is a cool star, also known as an M star or a red dwarf. You might have heard these in the media. And it's red because it's cooler than the sun, but because it's cooler, the habitable zone is much, much closer in. Okay, so the time that it takes the planet to go around is in fact much, much shorter than our 1 year. Okay, why did this restart? Hold on, pardon me. Let's go to the next slide. Sorry, I'm just trying to figure out where my slide went. Okay, my movie did not want to stop. So in order to catch you all up on 3 decades of planet hunting. So the first exoplanet was discovered in the late 1980s by my PhD advisor, Gordon Walker, up in Canada, and his collaborators. And so I'm not going to go through all the exciting discoveries that we've had in this field, but just mention the 4 most important ones for our purposes here. One is that exoplanets are everywhere. And when I mean everywhere, I mean seriously everywhere. It turns out, thanks to NASA's Kepler mission, that on average, every star hosts at least 1 planet, which is kind of a remarkable thought, right? I mean, just think about it. When you look out into the night sky, probabilistically speaking, every one of those stars has its own planets, right? And in fact, it's actually more than 1 planet per star, which means there are more planets than there are stars in our galaxy. So when you think about that, our galaxy has probably 200 billion stars. There are more than 200 billion planets in our one Milky Way galaxy, right? And there's actually 100 billion galaxies in our universe. So the planets are everywhere is indeed true. They're extremely diverse. So if you think about all the planets in our solar system, right? Earth and Mercury, Venus, Mars, Jupiter, Uranus, Neptune, and so on. They're very different from each other, right? Some are gas giants, some are ice giants, some are rocky, some are volcanic, some are not, and so on. But the range of diversity amongst the exoplanet population is in fact even greater than what we imagined if we were basing things off of our own solar system. Of those 4,000 currently confirmed planets, we have 20 that we know are in the habitable zones of their own planets. And that's counting. We're still finding more, and we're still characterizing more. And it's only really a matter of time until we find more and more and more. Then if you work out the statistics further, and you then say, okay, if we know how many of these cooler stars there are, like Proxima Centauri, these M dwarfs, right? They're lower in mass than the sun. They're about half a solar mass or smaller. And you work out all the numbers. It turns out that of those greater than 200 billion planets in our galaxy, 40 billion of those are rocky planets in their habitable zones. 40 billion. Now, I can't see your faces, and I really hope they're surprised, because this is not information that we had just a few years ago. This is really brand new. You may have heard this from Ariel last week, so I guess maybe you're not surprised now that I think about it. you probably already heard this, but it's still an amazing time, I think, to be studying astronomy and even just existing as a human on a planet, thinking about how the chances of us truly being alone are really quite small. So to orient you about these small stars, here's an image of our sun, which may be familiar to you. And an M dwarf is smaller. This is just a cartoon, because unlike the sun, this is an actual photo of our sun. We cannot really take photographs at this detail of M stars because they're just too far away. Even Proxima Centauri, our closest one. But just to give you a sense, they're cooler, they're redder, they're smaller. Here I'm plotting the luminosity, so the energy that the star emits is a function of mass, and this is on a logarithmic scale here. And here's the sun at 1/1. These numbers are all relative to the sun. And Proxima Centauri lies way down here at only 0.2% of the sun's luminosity. So it's very faint, and as I said, the planet therefore has to be much, much closer in to the star. And it turns out that Proxima b, the planet, in order to stay warm enough for liquid water, it has an orbital period, so its year is only 11 days. It takes 11 days to go around. So if you were living on that planet, your birthday would be every 11 days, which some might not complain about, and some might, I suppose. They're also the most dominant planets in our galaxy. 75% of all the stars in our galaxy are these M dwarfs. So when someone says to you, the sun is just your average star, it's in fact not your average star. These red dwarfs are the average star. Okay, now let's go to how we're going to detect these planets. So I told you there are 2 successful methods. There's actually 5 successful methods, but 2 that are really cleaning up, 2 that are doing the most work, the heavy lifting. The first is the transit method. And here I'm showing you brightness as a function of time. And conceptually, it's very straightforward, right? You have a planet, cuts in front of the star, and you see the light that's blocked out by the planet drops your measured light by a certain amount, and then comes out the other side. So it's pretty straightforward. And in fact, we see this in our own solar system. Here, as an example, is the images of the transit of Mercury that happened a few years ago. 5 years ago, you can see people took different images of Mercury as it cut in front of the sun. We can also use this transit method to study the atmospheres of these planets. And it is this idea of the transit method where you can look at the spectrum. So the spectrum is the light broken up into all its different wavelengths, right? You get the rainbow from the sun. When you see a rainbow through a prism, right? It's actually the spectrum is what we call it. And when you see a spectrum through this transit method is when you can actually start detecting different gases in the atmospheres of these planets. So we've already detected plenty of hydrogen and plenty of water, pardon me, in giant planets. We have yet to detect water in the atmospheres of small planets, but people are working hard to do that. And I think it's only a matter of a couple of years before that is done. So this is the main technique by which, at least in the near future, in the next couple of decades, we will be looking for gases that are what we call biosignatures in these planets. So these are gases that are created by the surface life on the Earth. Now, there is a challenge with the transit method, and that is that you need to have just the right geometry from our perspective on Earth, or from a telescope orbiting Earth, that the planet cuts right across. And it turns out that only about 2% of orbits will allow this to happen. So if you want to catch all the planets, right, because the orbit could be tilted, you may not get a transit, right? And then you'll be missing 98% or so of all the planets because they don't happen to have this perfect inline geometry. So the method we use in order to catch all the rest of these, because we don't want to miss them, is called the radial velocity, or the Doppler method. This was in fact the very first successful method back in the late 80s, was done this way, not through the transit method. And essentially here what's happening is you're measuring the light from the star, because remember, most of the light is coming from the star. The planets are very, very faint. So we're not really detecting the planets directly with this method, but what you are directing is its gravitational tug on its central star, right? So they are both orbiting a common center of mass. And so you can see this tiny pull. And in fact, Jupiter, because it's so massive around our sun, does have a tug on our sun that would be measurable if an alien civilization had the same technological capabilities that we have now. And the way we measure this velocity is by, again, looking at the spectrum of the star. We break it up. We see all these dark lanes, which are from different gases absorbed in the star's atmosphere, and watch it move back and forth, right? So it's red shifted when it's moving away from you, and blue shifted towards the blue end when it's moving far from you. Now, I wish I could see your faces to know if I've lost you or not. So certainly, maybe I'll pause here for any questions with regards to the detection techniques.
Friends, feel free to unmute yourself or write your question in the chat.
I can see you now. Does anyone have any questions? What, anything so far?
Great, let's keep going. Awesome.
You're doing a very nice job, and
So clear.
this is
So
much
clear.
clearer than I've seen before.
Thank you, Michael. I appreciate that. Okay. Let's see, then we will keep going. Here we go. All right, so now I'm going to tell you about a really exciting program called the Pale Red Dot that first discovered the planet Proxima B around Proxima Centauri. Here I'm showing you the sun. Then the Oort cloud is this cloud of stuff that kind of is still bound gravitationally to the sun, 2 light years away, 4 light years away. So this is where Proxima Centauri lies, right? It's our closest star. It's at about 4.3 light years. It's part of a triple system where Alpha Centauri A and B both are. So you may have heard of Alpha Centauri. It's been very popular in the, I guess, the science fiction world. But really, we're looking here. And these two, we actually don't know if there are planets around these two. People have been looking, but have not yet found those planets yet. But of course, we're most excited about these closest stars, because if we know the planets are there, then those would be the first ones we would ever go visit. Maybe not with actual humans, but with robotic missions and tiny little cameras, which I'll talk about at the very end. So that's why it's particularly exciting to be talking about the nearest ones. This is a video just showing about the telescope, this big telescope here, which is actually not so big. It's really a relatively small telescope by modern standards. But using a relatively small telescope, the team was able to measure this radial velocity signature. So looking at the star moving back and forth due to the gravitational tug of the planet, of the small planet, right? And they were able to discover a tiny Doppler signal, a tiny radial velocity signal. That signal is 1.4 meters per second, right? Oh my goodness, I don't know what that is in feet, because I'm Canadian and I don't think in feet quite yet. But if you have, imagine 1.4 meters, and let's call that, was that 5 feet or so, you could walk that at a pretty good clip, right? So what we're doing that is we are in fact measuring a star that is an entire star moving at the speed of a human walking. Just imagine that, we're just walking. And that's this giant, that's just a human walking. Then you have a star moving at that tiny little speed, and we're able to measure it from 4 light years away. I mean, I find that phenomenal. And whenever I've been at the telescope and measured these kinds of things myself, because I have detected planets, I have measured this particular measurement myself. I'm always kind of fascinated, especially because this 1.4 meters is not our detection limit. In fact, we can now measure the motions of stars to 20 centimeter precision, 20 centimeters like this per second. Just imagine something the size of our sun that we can measure to this tiny velocity precision, because physics is so spectacular. Okay, so that was just a sidebar of my enthusiasm for measuring stellar velocities. So Proxima B, we found out through these measurements, is about 1.3 Earth mass, so it's probably rocky, and it's at an orbital distance of only 5% of an astronomical unit. That's the distance between the Earth and the Sun. So we are 1 astronomical unit from the Sun, and Proxima B is only 0.05 astronomical units from its host star, with an 11-day orbit.
Professor, there's a question in the chat. Is it okay if I ask it now?
Please.
This is from Andy Elliott, and he asked, what are the statistics for interstellar distances in our galaxy?
What are the distances of the planetary distance from its star, or the distance from us?
It just says interstellar distances.
Interstellar distance. Well, okay. So our galaxy is in the image that I showed you. I'm going to, and Andy, feel free to unmute yourself and clarify if you like. But here we have.
I was asking about what typical distances are between stars. You know, we have these 3 closest stars at somewhere between around 5 light years. Is
Right.
that typical distance between stars in our galaxy, or are they really close or really far?
That's a good question. There's a distribution, because stars are created in clusters. They're created in giant clouds. And so sometimes those clusters have 100,000 stars very, very close together. We call those globular clusters. Sometimes we have stars, clusters like the Pleiades. Do you guys know the Pleiades up in the sky? That small constellation of the 7 sisters, but it actually has hundreds of stars. You just can't see them all with your naked eye. Those are all clustered together over hundreds of parsecs, or I'd say thousands of light years. Our sun happens to be alone. We don't have a partner, but more than half of the stars do have partners. So the fact that we are alone is less common than your typical star. So Andy, I don't think I answered your question explicitly, because there's actually quite a variety. Okay, and also it changes with time, because stars are constantly moving. So there's evidence that we were near another star that went supernova at the beginning of our solar system as life, but that star has moved on, or it exploded, and the white dwarf component of it moved on. So it's hard. I can't give you. I can give you a very detailed answer, but not a easy answer. Let's put it that way.
Okay.
There's nothing weird about these stars being close to us or that far to us, if you consider 4.3 light years close or far. Again, it's all relative. If we were part of a star cluster, that would be far away.
Just one question in terms of the closeness. When we talk about climate change and the damage we've done to here, have we done damage beyond here?
No.
Okay. Thank you.
Our damage might extend to our low Earth orbit. If you want to talk about polluting low Earth orbit with a bunch of small satellites, human-made small satellites, that's a conversation that one can have about polluting of the near Earth space. But we have not really polluted anything else.
Okay.
In that sense. Okay. All right, so then the key question that we want to talk about is Proxima B habitable? So the question of habitability of these planets It depends on both the stellar properties and the planet properties, right? We on Earth here are habitable because we have water, right? And we have an atmosphere and we have the right conditions on the Earth. But a lot of those are also connected to the star, which is why one reason why, as Rabbi Shmuley had introduced me, I study star-planet interactions, because it's actually the holistic view of the planet properties and the star properties that control habitability. It's never just the planet in isolation. And then if you really want to dig down to the details, right, you can think about all the different parts of the star that I list here in this word cloud, and all the different parts of the planet that matter. And this is an entire new field, not so new, but over the last couple decades, called astrobiology. And the astrobiologists delve into typically one or two of these, but most people don't deal with all of these because these are highly specialized fields. And even I, who am, by training, a stellar astrophysicist, I usually study the stars and the planets kind of in their interaction. I am learning a lot about the Earth's climate and the Earth's atmosphere and the Earth's volcanology because I'm trying to stitch all this together. So it's been very exciting from a career standpoint to really start delving into lots of other fields in order to understand this big question of habitability. But a lot of my work focuses on the interaction, as I said, with the star and primarily with stellar activity. So here is a movie of our sun during a flare, and our sun is a relatively quiet star. Most stars in the galaxy are much more active and flare much more frequently than our sun. And so if you think about, especially these low mass stars, they have super flares, which are giant flares, every day for the most part. And so you really have to think about what is the environment in which these planets are actually exposed to. Another thing I think about often is the magnetic field of the planet, because in this kind of environment where the sun can have a giant explosion, you might strip off the atmosphere, which is what we think might have happened to Mars, and why Mars is no longer habitable, because it did have a magnetic field that shut off at some point, and therefore most of its atmosphere has been stripped away by the sun. And so I think a lot about planetary magnetic fields. In fact, my PhD thesis was looking for magnetic fields on other Jupiters outside of our solar system. So the answer to the question, is Proxima B habitable? Well, it's complicated, right? What do we know so far? We know that the planet's there. We know that it's roughly Earth mass. We know what its surface temperature probably is, because we know the temperature of its star and we know the distance to the star. And that's about it. We roughly know its age, right? But we're still working hard to understand what its stellar environment is. We had a large program with the Hubble Space Telescope in order to monitor the flares off Proxima Centauri, the star, so we could try to answer some of these questions. People are trying to figure out how to get atmospheric composition of Proxima B, because it does not transit. So we now have a tougher job as to figuring out what's in the atmosphere of that planet. So the answer is we don't know if it's really habitable. It has the potential to be habitable with the first few ingredients that we know of, but I cannot say for sure one way or the other. But since it is our absolutely closest exoplanet, in fact, the closest planet that we will ever have, the closest exoplanet outside of our solar system, there has been effort put in to trying to get there, right? So sending humans there at the moment seems impossible, right? We're still working hard to get humans back to the moon and then over to Mars. And that's really just next door compared to where Proxima B is. And so this is a program out of UC Santa Barbara. A professor there is working on, along with a breakthrough Starshot group, if you've heard of them, and they're investing a lot of money into sending little tiny cameras that are about the size of your fingernail that will be accelerated to a higher fraction, or about 20%, which is fairly high, a fraction of the speed of light. And so you can accelerate a little tiny camera to go very quickly. So even at 20% the speed of light, it would take about 20 years for this little tiny camera to get from Earth to Proxima B, given that it's 4 light years away. And then it could take, the plan is for it to take pictures and tell us more about what the atmosphere and the surface of this planet might be. And then it will take 4.3 years for the data to be sent back, because the data is coming back at the speed of light. So maybe in 20, 50 years from now, we will have actual pictures of Proxima b. So that's very exciting, even though it feels like a very long time away. So I want to leave you with this idea that if you take one thing from this talk, is that to look up at the night sky, you're not looking at stars anymore. You're looking at complete stellar systems out there. So I hope that tonight looks clear where I am. If you go outside and look at the stars, you'll have a whole new view of what the night sky truly is. So I'm gonna stop there. And now we can turn the conversation to answering any science questions that you have, certainly, but then also have a conversation about what does it mean to you if Proxima Centauri b is in fact habitable and perhaps even inhabited. So thank you.
Awesome. This was so clear and so interesting. Thank you so much. And I'm sure indeed we have many questions, as do I, but I will step back to hear from some others first.
I have a question.
Sure.
Would it not be easier to consider Mars and somehow or other recreating an environment that humans could live on, because we can reach it a lot sooner than our nearest star?
I think, A, that's an excellent question, and B, that also answers my question to you, because what it sounds to me like is you'd be interested in humans living on another planet. What is the potential of humans living on another planet? Which is a fascinating part of the search for exoplanets. You're 100% correct that going to Mars is much easier. If you go back to the habitability, or the climate challenge that Rabbi Shmuley asked about a few minutes ago, I also think it's much easier to fix our issues here on Earth than creating a habitable environment on Mars. So I personally have very little interest in creating a habitable environment on Mars. I think it'd be great to go discover it as a scientist and to look there, but as a civilization to move there, it's way easier to clean up our mess here. I think it's a very hard problem over there.
Okay, I'm sorry, I cut you off.
I just want to finish. The second part of the question there then is, for these exoplanets, really the question is studying whether they are habitable and inhabited more than will we ever go there and live there. At the moment, we're not trying that because, as you point out, Mars is much easier and it's right down the road, right? So, okay, yes, Rabbi.
Okay, awesome. So in Jewish mysticism, the assumption is there's a center, and the center is God. And the rest of us are interconnected, and to that center. We are sparks to that one bonfire. We are souls with a prayerful channel to the center. Now, when all we talked about was a sun and everything orbiting around the sun, there was a center. But when we have exoplanets that rotate around their own stars, I guess my question now is there any center of it all? Or is everything decentralized? And what does that mean for you in terms of how you think about your theology in relationship to kind of the organization of space?
Okay, I'm going to get into a little cosmology here, which
Right.
I don't know how to talk at all about. So first of all, okay, on a personal level, the center for me, as you say, is the entire universe. And we are just like in mysticism, right? We are all sparks of God. We are all within God. We are all within the universe, which we are physically and potentially spiritually. If you want to tie it to a potential physics concept, the universe can be described mathematically as infinite, right? Infinite in all directions. Started from the Big Bang, it's off, the space has gone on infinite in all directions. When you have infinity in all directions, there is simultaneously no center and everywhere is the center. So you can choose how you want to relate to the universe. I like to think of it both simultaneously. I understand it's a dichotomy, but if you have, it's kind of beautiful. It's kind of beautiful in the same sense of where we're taught to be proud, but not so proud. You know, the whole Mount Sinai, why the Torah was given on Mount Sinai, right? And not on a huge mountain, but not in a valley, right? We have to be proud of our accomplishments. So it's kind of like that, where you can feel like the center of the universe, but you shouldn't be the center of the universe. But in reality, you are the center of the universe, so that you then have the power, the confidence, and the inclination to affect the world. That's how I think about it.
Wow, thank you. Someone else, please jump in when you're ready.
Well, when you talk about habitability, are you talking about the physical makeup of the planet? And then you look at that, you look at the age of the planet too. For example, if the universe is what, 13 billion years old, and we had say there was an intelligent life on a planet that existed 7 billion years ago, or 2 billion years in the future, isn't that even more complicate the whole figuring out about life?
You're 100% correct. And I'm not sure if in my word cloud I have age in there, but if I don't, I certainly should, because yes, age is right there. Do you see it at the bottom?
Mhm.
Do you see that? Yeah, you're 100% correct, because on our planet, life did not exist for the entirety of the planet. Also, not only did the Earth evolve over time, but the sun evolved over time. So the sun, stars have a very interesting evolutionary life in and of themselves. And at the very young ages, at the time that this Earth was first forming, the sun was much more active, had many more of these super flares, and an Earth around that kind of young sun would probably not be habitable. So you're 100% correct. And when people do look for habitable planets, they intentionally look for old stars, because old stars mean that the planets are old also, because they form roughly at the same time.
And one other question, and when you say looking for life and the properties, are we looking or assuming oxygen and water-based life, or is there speculation for other?
That's such a good question, and people are working hard to figure out ways to search for life as we don't know it. And you are correct that we are being very narrow, and by we I mean most of us, not everyone. Most of us in this game of looking for life on other planets are very much focused on life as we know it, because we don't know what else to do. There are people, clever people, even at ASU. My colleague whose office used to be next door to mine, her name is Sarah Walker. She's a theoretical physicist, and she works in this realm of devising life as we don't know it, and trying to understand the work that she does really goes from theoretical physics into philosophy. She's really working on this boundary, because it's a hard question to ask of how you would identify it. I could send you to some of her talks. I wouldn't do a very good job trying to explain how she plans to do it. She works on the idea of chemical networks. The fact that that our atmosphere is chemically stimulated by life that would be independent of a carbon-based life. It's fascinating. It's really fascinating stuff, and I'm not going to do it justice, but you could just invite her or catch her. Her name is Sarah Walker. And so, yes, there are few brave people out there trying to figure that out. And the rest of us are more practical and just trying to look for oxygen, methane, methane and water. Seems so practical, the rest of the world thinks that we're, wasting our time at some level, but compared to those guys, we're really grounded. Yeah, Chuck.
Rabbi. Yeah, I actually have a question for Rabbi, based
Yes,
on the
please.
discussion you guys just had in the
Yeah.
previous question about the center of the universe. So Rabbi, does our theology describe humans as the center of, say, the universe, or does it imply it because that's human beings' frame of reference? You know, we really don't know what about the universe. We know something about it, but we really don't know, right? So
Yeah.
I'm just curious what the assumption is in our
Yeah.
theology.
Yeah, it's a great question, and and as usual, it's a debate. And the easiest way to frame the debate is between Rav Sadia Gaon and Rambam, Maimonides and Rav Sadia Gaon, where Sadia Gaon really did embrace much more of an anthropocentric worldview, that humans are the center of existence, of reality, and everything is moving outwards from the self, from the pinnacle of all creation. Whereas Maimonides thought that centrifugal versus centripetal, that what was moving outwards and what was moving inwards, and Maimonides thought that humans were really not the center. And there's really a lot to unpack there. And then you get to Chassidut, where the founder of Chassidut, the Baal Shem Tov, says that the reality is really where the mind is, where the soul is. And then you have to ask the question, well, where is the soul? Is the soul in the mind in the Platonic sense? Is the soul something beyond the body? In which case, where is that located in any sense of space? And so I guess there's kind of three different ways I would approach your question. One would be morally, kind of where is the center when we think about ethics? Where is my center of care? And there, Elie Wiesel famously said, the ethical center is wherever the greatest suffering is at that time. So from an ethical perspective, the center is where tragedy strikes. Then there's the God-centered question is where, if the essence of a human being is created b'tselem Elohim, in the image of God, where is that tselem? Where is that image? And wherever I find that, whatever capacity of humanity, is where we would locate kind of the godliness, the God center of human experience. But then perhaps the third is within not the, let me take one step back. In the Sefer Yetzirah, the work of Kabbalah, there is, it says that three things were created at creation. There was the realm of space, that's called Olam, the realm of time, that's called Shana, and the realm of soul, Neshama. And so if you almost look through those three spheres, are we looking at the center through space, which is the way we've been approaching this? What is the center through the sphere of time? Like at what moment is there a center? Or then there's the spiritual realm, which is beyond the material realm. And where do we find a center in the realm of spirit? And so I don't know if I've said anything helpful at all, aside from just throwing a few different models out there. But I guess the easiest thing to say is it's a big debate. It's a big debate, and where the center is and what that means for how we live our lives.
It just bends your mind, obviously.
Yeah.
But if there was other life, other intelligent life, maybe not human, and probably maybe wouldn't be human, it would be whatever life evolved to be in that other place, then it's interesting to think about what you just said in terms of that. And from that point of reference, that could be the center. Or maybe what you described applies to us and whatever life there is. It seems like it would.
Well, it's interesting. You kind of remind me of when I was a graduate student, first becoming more observant in my Jewishness. I went to a lecture by Rabbi Dr. Vevel Green. I don't know if you all know him. He was an Orthodox rabbi, but also a scientist. And so, of course, I was at this lecture when he came to town in Vancouver. And I asked him if what Judaism says about extraterrestrial life, beings. And his answer was, if I recall correctly, that there's no problem in Judaism to have extraterrestrial life, even extraterrestrial humans. They just can't be Jews, because the Torah was created uniquely for this planet, for these Jews on this planet. And so, so it would not be a crisis of faith for us if extraterrestrial life was discovered.
Yeah.
That's the answer I got. I'll stick to it.
I like it.
Yeah, Chuck, just to say one last thing before we open it up again. One interesting psychological read on human history is the longing for a center, right? And the choices we make in our lives, how we organize a home, how we organize a society, the need for hierarchy. And if you look at kind of the evolution from monarchy to democracy, and how family structures change, like what is this desire for, or spiritually and psychologically, for centers, and how we organize our reality.
Yeah. Thank you.
Who else has a question for Professor Shkolnik? Okay, I've got one. Does doing this work give you more or less of a sense of yira, a sense of mystery, awe? When I'm, as a typical person, I go with my kids outside, we look up at the sky and we're like, this is amazing, we're blown away. And we just like stare at it. Do you, because it's a science to you, it's a work for you, do you feel more or less spiritual awe and wonder in how you encounter the space?
Certainly more, because, but more in a way you may not expect. Not because the universe is so spectacular and the scales are so huge, both time scales, spatial scales, energy scales. It's true, everything on astronomical scales is spectacular. It goes from the tiny, like little subatomic particles to the size of the universe. So I get to think on very huge scales on all axes. But the part that is most impressive and most awe-inspiring is the fact that I, just some random woman living on Earth in these few years of the Earth's history, am able to contemplate that and understand it. That's the most awe-inspiring thing to me, right? Because it's so spectacular. Who am I to even understand this? The fact that it is knowable is the most interesting thing to me. Spectacular. I don't know. I love it. I love my job. I guess I have a question for you guys. Is how would you react, or would you care if you read a New York Times headline that said, astronomers have found extraterrestrial life on Proxima B, confirmed? Because there's going to be a lot of false claims, don't worry. Before we get there, there'll be a bunch of false claims, but at some point, something will be confirmed in a believable way. And would that matter to you? What would you think?
This would be a massive moral crisis for me.
Really?
Massive. Because if there are sentient beings that have sentience, then we have a moral responsibility to address their suffering as humans and as Jews. And that means we have to rethink our resources in terms of how we respond to the needs of other forms of life.
How do you know they're suffering?
Well, we'd have to know that. But my presumption is if there's consciousness, the question would be consciousness.
Okay.
What do others think?
I take a different perspective, totally. Yeah. I see in the infiniteness of time and the infiniteness of space, I cannot believe that we are the only sentient being that's ever existed or ever been, because our own particular insignificance, because of the infinity of which we exist in, and so I'd be surprised. The question is scale and time and space, if we ever would know about each other, or be able to interact with each other.
Yep, so true.
I have a question.
Mhm.
There was a astrophysicist at ASU, he's no longer there, Lawrence Krauss, who wrote A
Mhm.
Universe from Nothing, which it was popular and a kind of a fun read and an easy read. But he's a self-proclaimed atheist, I think, of our heritage. But the conclusion of the book was there's good news and bad news, that the universe will collapse upon itself in 3 or 4 trillion years. I mean, the bad news, the universe will collapse upon itself, but the good news in 3 or 4 trillion years. So that was kind of left me in a quandary. And just like as you expressed about yourself, who am I to be, and you're such a brilliant woman, apparently. But it left me with the question is, so what's the difference? In other words, you're doing all that you're doing, but ultimately, but maybe that's too long of a time span, you know, for the human concept, for somebody like me to get. But how do you, I mean, you're in this field and some of your colleagues believe in God and are religious in the sense that you are, and kind of a melding of the spiritual with the scientific. But then there must be many of your colleagues that are fatalistic like that. So I'm just wondering how you deal with that.
That's really interesting that you say that, especially about Lawrence Krauss. So you've tied. So it is true that I would say most astrophysicists would probably say publicly that they are atheists, which in itself is a non-scientific response, because an atheist would say there's no God, and I don't think there's any evidence that there's no God. We can debate about evidence of God existing, but there's no evidence that I know of that says God doesn't exist, right? I don't, if you know of God, but I mean, I don't know if there's evidence that God exists for sure. It's not hard proof. I mean, we can talk about it, and there's lots of theological books trying to use logic to prove God's existence. And maybe some of you have read those. I've read a few of those myself, but there's certainly no evidence for the lack of a God. There's no physical evidence for that. So it's hubris to assume that there is no God, first of all. Or to say, I shouldn't say not to assume, but to say that for sure there isn't. One could say, if one says I'm agnostic, I can totally buy that. Oh, I'm sorry, you took your video away, Anita. I was enjoying.
Oh, I'll come back. I'll come back.
So first of all, so it is a challenge because I do, thank you. It's just much more pleasant this way.
We have a lot of activity going on in the background. So.
Oh, I see. No, whatever you're comfortable with, Anita, whatever you're comfortable with.
Okay.
So how do I deal with that? I guess I don't really deal with it head on because it's such a personal question. I don't debate people's belief systems with them. I just don't do that. I think it's too personal. And also the human ego plays too much of a role in it, that it's a hard thing to converse with people who are so sure of something, which is, I think, a very non-scientific method to address the question.
And how can we debate the existence of God if none of us know what we really mean by a God?
Well, that's why it's kind of personal. I mean, we have the Torah, we have Maimonides, and even Maimonides in his books completely changed the relationship humans had to God, right? And already Jews had existed for what, a few thousand years already by the time Maimonides came around. So Jews had, so we are still evolving in our thinking collectively in our relationship with God. So collectively we're evolving, and certainly personally, one-on-one, everyone is thinking through and changing ideas. So it's a really hard question. I actually just don't do it, Anita, especially with the kinds of people who are self-proclaimed staunch atheists, because I don't think they're thinking carefully about it at all. I think they are developing a non-scientific truth for themselves that resonates for them. And that's great. That's their own personal path. I just don't
Okay,
knowable.
friends.
We can have a
so
woman to woman talk someday.
Sure, anytime.
this is a fascinating place to pause on. And I want to invite friends tonight. We have a panel from 3 of our Arizona Jews for Justice fellows who are speaking about LGBT issues in the community. That's tonight at 6. Also on Monday, we'll be learning with Noam Sion from Hartman on the topic of Jewish debates about marital intimacy. In typical Noam Sion fashion, he's asked everyone to learn the sources with a chavruta before the session. So if you sign up for that, make sure you get those sources in advance from us so you can learn that. Our next Science and Judaism session will be on the topic of awe, perspectives from psychological science and Jewish tradition, from Professor Michelle Lani Shiota. Professor Shkolnik, this has been so fantastic. Thank you so much for this gift of your time and opening up this world to us.
Yeah, thank you.
Have a great day, everyone.
Thank you. Take care.